In this video, we're going to be doing some examples where we orthogonally diagonalize matrices. So here is the example. We want to find an orthogonal diagonalization for each of the following matrices, or explain why it's not possible. So in part A, we have this matrix, 1, 2, 2, 4. So to check to see if a matrix is orthogonally diagonalizable or not, I need to check to see if it's symmetric. So let's form the transpose. So for the transpose of this matrix, the first column, 1, 2, becomes the first row in the transpose, so 1, 2. And then the second column, 2, 4, should become the second column of the transpose, so 2, 4. Alright, so we have this. So looking at our two matrices, they are the same. A equals A transpose, which means my matrix is symmetric. So because it's symmetric, that means it should be orthogonally diagonalizable. Diagonalizable. It's awesome. So at this point, we've determined if it's orthogonally diagonalizable or not. Now it's a matter of just doing it. So to do that, we begin by our normal diagonalization process. We find the eigenvalues and eigenvectors. So find the eigenvalues and eigenvectors. So let's begin by looking at the characteristic equation. So I need the determinant of A minus lambda I. So I'll write some vertical lines to indicate I'm taking a determinant, and then I have 1 minus lambda, 4 minus lambda on the diagonal, and the other entries are both 2. So if we evaluate this, if we multiply the 1 minus lambda times the 4 minus lambda, we'll get lambda squared. We get a minus 4 lambda, a minus lambda, a minus 5 lambda, and then a plus 4. And then from multiplying the 2's together, we'll get 4, and we subtract that 4. And we need to set this equal to 0. So what we have is we have lambda squared minus 5 lambda equals 0, and if we factor, we get lambda times lambda minus 5 equals 0. So at this point, we know what the eigenvalues are. We know that lambda equals 0 or 5. Those are our eigenvalues. So let's find eigenvectors now. So maybe first we'll do it for lambda equals 5, and then afterwards we can do it for lambda equals 0. But it doesn't really matter which order I do it in. So for lambda equals 5, I would look at A minus 5i. So A minus 5i. I subtract 5 from these diagonal entries. So 1 minus 5 gives me negative 4. 4 minus 5 gives me negative 1. The other entries stay the same as 2's. Alright, so with this matrix, row reducing it isn't too bad. So I'm actually just going to tell us what the final row reduced form of this is. But one thing to notice is the two rows here are multiples. If I multiply the second row by negative 2, I get the top row. So because of that, in the row reduced form, one of the rows should just become all zeros. And then the other row, I can quickly see what it is by just taking the top row and trying to make this negative 4 become a 1, which I could do by dividing by negative 4. So that would give me 1, and then negative 1/2. That's what it row reduces to. So if I write the equation for the top row, we get x1 equals 1/2 x2. So now if I write down my answer as a vector, so we get x as a vector. So the first entry, so it's going to be x1, x2. x1, we know what it is. It's 1/2 x2. And x2 is free, so we leave that how it is, as x2. And if we factor out the x2, we get x2 times the vector 1/2, and then 1. So at this point, we could take 1/2, 1 as an eigenvector. But it's going to be a little bit nicer if I decide to scale it and get rid of the fractions. So let's scale by 2. We're allowed to scale eigenvectors by a non-zero number, and they stay eigenvectors. So my first eigenvector, I'll call it v1, is going to be 1, 2, because I've multiplied this by 2. So now we have to do this for lambda equals 0. So I've gone ahead and done that. I've gone ahead this time and actually done the whole rule reduction for lambda equals 0. And for this one, we didn't need to scale the eigenvector. It was already integers for the entries. We already had integers in the entries. So the second eigenvector is -2, 1. So one cool thing about this, is if we take the dot product of these two eigenvectors, so v1 dotted with v2, so I'll get 1 times -2, multiplying their first entries together, plus second entries multiplied gives me 2 times 1, 2 times 1, so -2 plus 2, that's 0. That means that v1 and v2 are orthogonal. So recall from the last video, that should be happening. We showed in the last video that whenever we have a symmetric matrix, like we did here, that the eigenvectors that come from different eigenspaces are always going to be orthogonal. So that's true when my matrix is symmetric. Alright, so let's keep going now. So there's something I want to be careful about. So we're trying to orthogonally diagonalize our matrix, which means when we write A in the form P times D times P inverse, that should be equal to P times D times P transpose. In other words, P inverse is the same thing as P transpose. And the reason for that is P is supposed to be an orthogonal matrix, because we should be able to orthogonally diagonalize it because A was symmetric. So if we try to just form P right now, using the eigenvectors that we had, so those were, I think it was 1, 2 for the first eigenvector, and then -2, 1 for the second eigenvector. There's a problem with this. There is a problem with this. So remember, an orthogonal matrix means it's square and it has orthonormal columns. So we want P to have orthonormal columns. Orthonormal, underline that twice. Orthonormal columns. But this P right now, if I were to just form it right now, is not an orthogonal matrix. It's not an orthogonal matrix because the columns are not unit vectors. Not unit vectors. Because they don't have length 1. Okay, so we need to normalize them. So that's our next step actually. We can fix this by now just normalizing them. So let's do that for our first eigenvector. So I'll call this, after I normalize it, I'll call the new vector u1. So u1 is going to be v1 divided by the length of v1. In other words, I multiply by 1 over the length of v1. Okay, so if I take the length, so v1 is this first column vector, the length of this ends up being square root of 5. 1 over square root of 5 in the front. And then times v1, so v1 was 1, 2. So if we multiply the 1 over root 5 into this vector, we get 1 over root 5 and 2 over root 5. That's what that first eigenvector is after we normalize it. So for the second eigenvector, if we normalize that, I've gone ahead and done that work ahead of time, but it ends up being the same type of thing. The length of the second eigenvector also just so happens to be root 5 in this problem. So when we distribute that in, we get -2 root 5, 1 root 5 for our normalized eigenvector. Okay, so now that we've normalized these, we are ready to write down what P and D are. So this gives us, so now we can write A in the form P times D times P transpose, because P is orthogonal. It's an orthogonal matrix, so the inverse is the same thing as P transpose. So let's write down what these are. Okay, so the matrix P is going to be our normalized eigenvectors written as the columns. So the first one was 1 over root 5, and then it was 2 over root 5. The next eigenvector was -2 over root 5, 1 over root 5. I'm going to highlight these as well. So here's the first column, here's the second column, just so I can associate each eigenvector with the eigenvalues. That's P. The matrix D, so the eigenvalue that went with this first eigenvector was 5. And the eigenvalue that went with the second eigenvector was 0. So I have this diagonal matrix, so everything else is 0. So the 5 went with the first eigenvector, and the 0 went with the second eigenvector. Alright, so this is our matrix P, this is our matrix D, which means this last matrix should be the inverse of P. But because P is orthogonal, the inverse of P is the same thing as P transpose. And that's one of the things that makes orthogonally diagonalizing really nice, because it's easy to write down what P transpose is here. So the first column of P is going to be the first row of the transpose. So I'll have 1 over root 5, 2 over root 5. So that is going to be the first row of the transpose. And then the second column of P will become the second row of the transpose. So negative 2 over root 5, and then 1 over root 5. And let's highlight that as well. So that right there, that is how we orthogonally diagonalize our matrix right here. So typically when we do a problem like this, it would be fine just to write down P and D individually, but I wanted to just begin our first example with showing you what the whole thing would look like, and noticing that it's really easy to write down what P transpose is. Alright, so let's do another example. So part B, let's let A be this matrix, 1, 2, 3, 4. So we first got to check to see if it's orthogonally diagonalizable. In other words, is our matrix symmetric? Because that's how we check. So if we form the transpose, the first row becomes the first column. So I have 1, 2. And the second row becomes the second column of the transpose. So 3, 4. So if we look at these, A and A transpose, they're not the same. A is not equal to A transpose. So our matrix is not symmetric. And because it's not symmetric, that means it's not going to be orthogonally diagonalizable. So we actually get to stop there. So that's one of the things that makes checking for orthogonal diagonalizability nice. If our matrix is not symmetric, it's definitely not orthogonally diagonalizable. So it might happen that it could be just normal diagonalizable though. So it could just be diagonalizable. No. So it's not orthogonally diagonalizable, but it might be regular diagonalizable. Okay, so I won't go ahead and determine that, but that's just something to keep in mind. So let's do another example. So now let's do a 3 by 3 matrix. So let's say A is this matrix right here. So this 3 by 3 matrix. Let's first determine whether or not this is orthogonally diagonalizable. So by looking at this matrix, we can see that A is going to be equal to its transpose. When I look at all the entries that are sort of across each other, mirror images of each other across the diagonal, they're all the same. The negative 2 and the negative 2, they're the same. The 4 and the 4, and the 2 and the 2. So this is going to be symmetric. So because it's symmetric, that means it's orthogonally diagonalizable. This is orthogonally diagonalizable. Okay, so now let's diagonalize it. So for this matrix, to save time, I'm going to just say what the eigenvalues are and what the eigenspace is for each one. So this is something that you should check. So check this. So the eigenvalues of this matrix end up being negative 2 and 7. One thing to keep in mind is in this matrix, when we figure out the eigenvalues, we're going to end up needing the rational roots theorem to help us factor our third degree polynomial that we'll end up getting. Okay, and now let me go ahead and write down the eigenspace for each of these eigenvalues. So the eigenspace for negative 2, which I denote as E sub negative 2, is going to be the span of the eigenvectors in that eigenspace. So the eigenvector in this eigenspace ends up being, I believe it's -2, -1, +2. So this is something we could check. We could go ahead and find the eigenvectors for -2, and we'd get -2, -1, 2. Or maybe a non-zero multiple of this. And then for the other eigenspace, so the eigenspace for 7, this ends up being the span of its linearly independent eigenvectors. So the first one is -1, 2, 0. And the second one is 1, 0, 1. All right. So the first eigenvector over here, I'm going to call this V1. And the other two I'll call V2 and V3 respectively. All right. So now that we have these eigenvectors in each of these eigenspaces, let's notice a cool thing. So the cool thing is that if you take the dot product of V1 and V2, so these are two eigenvectors from different eigenspaces, it ends up being 0, because I get 2 and then -2, and that's 0. And similarly, if we take the dot product of V1 and V3, those are also from different eigenspaces. That also ends up being 0. Okay. Next, I want to point out a major error that we sometimes make in problems like this. So I want to really point that out super explicitly, so hopefully to help us avoid making that error. So I've gone ahead and just copied down one more time what our eigenvalues were and what our eigenspaces were. So now let's talk about this major error. So major error. Double underline. Okay, so I'm going to make the major error, and then I want to give you the opportunity to pause the video and think about what this error is. So let me go ahead and put these vectors, these eigenvectors, in as the columns of P. So -2, -1, 2, that'll be my first column. And the other two eigenvectors, so I have -1, 2, 0, and then 1, 0, 1. All right, so at this point, pause the video for about 1 minute and see if you can figure out what the major error is that I've made. So my hint is there's actually 2 errors that I've made. So see if you can spot those 2 errors. So pause the video in 4, 3, 2, 1. Pause the video. Pause the video and really try to think about this. All right, so hopefully you did that. Hopefully you paused the video. If not, go ahead and do so now and think about this. So let's go ahead and talk about it together now. So one error, which you might have noticed, is that the vectors are not univectors. The eigenvectors are not univectors yet. Just like in the previous example that we did in part A. They're not univectors. But there's another more important error. Because the univector part, that's a quick fix. There's another more important error. And that's the fact that I think I forgot to write the 2 here. This was V2. So the second eigenvector and the third eigenvector, there's an issue with them. And the issue is they are not orthogonal. So the upside down sort of T was the symbol for orthogonal. And by drawing a slash here, I'm saying they are not orthogonal. And we could check that. If we take the dot product of these 2 vectors, we don't get 0. So V2 and V3 are definitely not orthogonal. So in general, the eigenvectors that come from the same eigenspace may not be orthogonal. Because we had a theorem that said if you take eigenvectors from different eigenspaces, like the V1 and the V2, they are definitely orthogonal. But the theorem didn't say anything about eigenvectors that come from the same eigenspace, like a V2 and V3. So that's posing a problem here. And that's why this was a major error if we were to write P like this. Okay, so P is actually not that matrix. So how do we get around this? Because we need to make these vectors orthogonal. So luckily for us, we've talked about a method for that back in chapter 6. And that is to use Gram-Schmidt. Use the Gram-Schmidt process. Okay, so one more time, I'm going to ask you all to check this. So I'm just going to state what we get out after we do Gram-Schmidt, because at this point we've seen some examples doing the process, and I want to focus more on just the overall method of orthogonally diagonalizing. So I'm just going to say what we get. So before we do Gram-Schmidt, the current eigenvectors that we have in that eigenspace are -1, 2, 0, and 1, 0, 1. Those were the eigenvectors that we have in this second eigenspace, -1, 2, 0, and 1, 0, 1. All right, so let's zoom it back in. All right, so these two eigenvectors, the problem with them is that they are not orthogonal. Not orthogonal. These are not orthogonal, so I'll even draw a sad face. We want them to be orthogonal, but these are not. So let's do Gram-Schmidt. So after we do Gram-Schmidt, this is where I'm just going to tell you what the answer ends up being. So the first vector stays the same when we do Gram-Schmidt. But the second vector, after we do it, will end up being 4, 2, 5. So 4, 2, 5. That is what we will get after Gram-Schmidt. And if we check these two vectors, if we take their dot product, we'll get -4 plus 4 plus 0. In fact, let me write that 0 a little bit better. 0. So these vectors are orthogonal. So these are orthogonal. And that's what we wanted. So now we're finally ready to form our matrix D and our matrix P. So let's form that. So let's form D and let's form P. So D is going to be our diagonal matrix that has the eigenvalues on the diagonal. So one of our eigenvalues was -2. And then we also had 7. And the eigenvalue 7 had multiplicity 2. And one of the ways I could see that is because my matrix is symmetric, the algebraic multiplicity always matches up with the dimension of the eigenspace. So these were the eigenvectors. I guess technically, initially, these were the eigenvectors that we got for the eigenvalue 7, and there's 2 of them in this basis. So we know that the algebraic multiplicity of 7 is going to be 2. So that's true for symmetric matrices. For symmetric matrices, the algebraic multiplicity of an eigenvalue is always the same as the dimension of its corresponding eigenspace. So now everything else in this diagonal matrix is a 0. And now we form P. So to form P, I have to normalize all my eigenvectors. So the first eigenvector was -2, -1, 2. It turns out the length of that vector is 3. So if we divide by 3, the first column of P will end up being, -2/3, -1/3, and +2/3. If we normalize these two vectors, so the other two eigenvectors, after we made them orthogonal, the length of the first one is √5, so we get -1/5, 2/5, and 0. And the length of this other vector is √45, so we'll get 4/45. We'll get 2/45. And we'll get 5/45. Okay, so let's just highlight these. So for the eigenvalue -2, this was its eigenvector. And then for 7, so for the eigenvalue 7, we had these two eigenvectors after we had done Gram-Schmidt and normalized them. Okay, so let's end the video with one more quick example that will preview the types of things that we can do after this with symmetric matrices. Sorry, just in general with matrices. So let's say A is the matrix 1, 1, 1, 1, 1, 1. All right, so is this matrix orthogonally diagonalizable? Sorry. So this matrix is not square. It's not even a square matrix. It's definitely not going to be symmetric. When you transpose this, right now this is a 3 by 2 matrix. If you were to transpose it, you get a 2 by 3 matrix, and that's definitely not the same. So because of that, because it's not symmetric, this is not orthogonally diagonalizable. So it's a pretty quick answer there. Not symmetric, so it's not orthogonally diagonalizable. But the reason why I wanted to include this example is to kind of preview the kind of things that we can do with matrices like this. So when our matrix is either not square, like this one, or if it's not symmetric, so if it's not symmetric, and we've seen two examples of not symmetric ones, one like this in part D, and one in part B, we can't orthogonally diagonalize it. So in fact, I said we can't orthogonally diagonalizable it, but I meant to say we can't orthogonally diagonalize it. But what we can do is, it turns out we can write A in the following form. U times, this is the Greek letter sigma, times V, where U and V are both orthogonal matrices, but they may be different sizes, because A may not necessarily be square. And this matrix sigma in the middle is really close to a diagonal matrix. It's almost diagonal, and it'll be M by N. But what it will have is lots of zeros. So putting matrices into this form is the topic of section 7.4, which is on the singular value decomposition. Singular value decomposition. All right. So in our course, because of time constraints, we are actually going to skip this. We are skipping this. So I wanted to mention it, though, for those of you who may take a future course that applies linear algebra, you may see the singular value decomposition. And if you take upper division linear algebra, you'll definitely see singular value decomposition.